and welcome back again on the same series of videos on electric circuits. So let us start. Last time we discussed about what do we mean by drift velocity and what is the current and how does current flows and what is the mechanism of current flow in conductors. So let us talk about a law which is known as Ohm's law. What is Ohm's law? So, this law is an experimental law or is an experimental finding by George Simon Ohm. George Simon Ohm, who was a German physicist or teacher, and he gave this law in 1826. This law was discovered, or these experiments were a series of experiments were carried out by Ohm in 1826 and he published it in 1827. So there is a very nice history behind this law. Is obvious you took this law or a very simple law as you take, but for Ohm this was not a very simple but very bad for this law. Ohm have to uh, bear lot more abuses and from very bad situations when he gave this law. So let us first take what this law is. According to Ohm's law, Ohm takes other different type of materials. All of them were metals, so different type of wires. Okay. And what did he did? He put potential difference, or he took some uh, voltage source, that is uh, he put some these wires in potential differences and measured the current or electric current through these wires. So what he found that the current through wire, that this current Vi and potential difference applied Vv. So this current I was proportional to the potential difference. What does this mean? That the current was some constant k times V. This means current was constant multiple of the potential difference or the voltage applied. When Ohm published this law, he have to bear abuses of many peoples, even from scientific communities and uh, also from the other peoples. Not even he have to bear the abuses, but also he have to go for the scientific or the teaching exile of the 14 years. 14 years later, or 14 or 17, I don't remember. So if it is 14 or 17, whatever it is, the Royal Society of the London, they also carried out these experiments and then they verified these laws. After that, Ohm came again in existence or in their scientific or teaching line. So is obvious or is simple this law looks, but for Ohm this was not so simple. He have to go from many bad situations. Even you can think a teacher have to exile or his teaching or scientific career for a single law, and this law again comes to, so how bad he would be feeling after that. So and we put this is V is equal to R times I. Okay, we don't write this in this form, we write in this form. and this R is called the resistance. It looks like something that is resist. This means uh, it resists in this way that there is a wire, okay, and this potential or the voltage be Vi at this place, and after this much of distance this voltage will decrease. So some, let this be V1, so this will be V2. So after that much of distance, if the current passes this much of distance from this metal, so this potential difference will be V2. And because in this difference is nothing but R times I, if where I is the current flowing through this conductor. So in this way we say that this resist. Okay, so this R is called the resistance. Now last time is I got the expression for the drift velocity and also about the current. So let us from that calculation or from that manipulations or that crude analysis, let us try to find out about this resistance, and also found that this resistance this resistance is proportional to the length of wire. Okay, if this resistance means if the length of wire is more, the less current will flow through it. Okay, and also it depends on the cross sectional area of the wire. This means resistance is inversely proportional to the cross sectional area of the wire through which the current is flowing. Now let us try to find, as we find here, Vd, that is drift velocity, is this much. Okay, so Vd is Ve times tau upon Me into L, and from here we found that this I is NEA times Vd. We take this value of Vd from here and put it here. So what we will find, I is equal to NEA times Vd. Vd is Ve upon MEL into tau. Okay, where tau is relaxation time, V is the potential difference, E is the current of electron, Me is mass of electron, L is the wire of length of wire, and A is the cross sectional area, N is the total number of free electrons per unit volume. So from here we get V is equal to MEL upon Ne square tau into this upon this into L upon V, L upon A into V. Okay, so this quantity, what I have done, this is I. Okay, this goes here, so this is I, and compare these two things from this experimental data and from our crude analysis. This R is MEL upon Ne square tau times L upon E. So from here it is clear that R is proportional to L and inversely proportional to cross sectional area. Okay, why do I say that this is a crude analysis? Because electrons for electrons we cannot use the uh, Newton's law of motion. It is very bad thing because electrons are the quantum objects. Okay, for that we have to just uh, talk about electric circuit and their analysis. So this is also not necessary to know, but if you learn, then you will feel enjoy that, oh, this is the way. So R is proportional to L and inversely proportional to cross sectional area. Now we define a term that is called specific resistance. So what do we mean by specific resistance? Specific resistance. Specific resistance we define is the resistance of a wire of L, that is 1 meter, and A is 1 meter square, or whatever this is, meter, or if this is meter then this is meter square, if this is centimeter then this is centimeter square. This means the resistance of a wire of unit length and unit cross sectional area is called the specific resistance of that material, not that of that wire but of that material. Why for the material? Because from here this expression we get, if we put L is equal to 1 and R is equal to A is equal to 1, we get that R is M E L, that is Me is the mass of electron, upon Ne square tau, Ne square tau, that is R specific. Whatever. Oh, one correction here. I have taken this L two times, that is Me upon Ne squared only. Okay, so this R specific will be Me upon Ne square tau, where N is the total number of free electrons per unit volume and tau is the relaxation time. Okay, so this specific resistance does not depend on the length of wire or cross sectional area of the wire. So this is characteristic property of each material at constant physical situation. This means if we don't vary the physical situations, this means if we don't vary the temperature, pressure, or etc., so the specific resistance of the wire or material will not change. So this is the characteristic feature which increases with temperature for the metals and decreases with temperature for semiconductors and bad conduct non-conductors. So in next time we will see how it changes with temperature and also something more. This is a specific resistance. If we, how do we define the uh, inverse of resistance, that is called conductance, and this specific resistance is also is known as resistivity, and inverse of this, or this is also defined as the conductivity. What do we mean by the conductivity? Okay, so how can I say that if we increase the temperature this resistivity increases? Because as we increase the temperature, mass of the electron will not increase or will not change, this thing will not change, but if we increase the temperature, then the know from kinetic theory, the chaoticness of the every particle, that is of every electron or the atoms, will increase. This means if these are the atoms, okay, they are vibrating. So if we increase the temperature, then the frequency of their vibrations will increase. So due to that purpose, electrons will move less distance between two consecutive collisions, so it will take less time between two consecutive collisions, so this tau will decrease. If tau will decrease, then 1 upon tau will increase. This means R specific, that is resistivity, will increase with temperature. So hopefully you will be enjoying, and take care.